Welcome to Lesson 11B, Tunnel Ventilation Analysis. Now we're going to analyze tunnel ventilation. We're going to concentrate on the balanced transverse ventilation system. We're going to do a control volume analysis of a little slice. This will be our little control volume. The key is to distribute all the parameters that we have, S, QM, QE, and we'll include wall losses as well, uniformly in X. We're going to approximate that C is steady and C equals C of X only. So as you go down this tunnel, there's continuous source of emissions from all these cars. We talked about how to distribute the S last time, and we'll do that also for the exit and entrance makeup air and exhaust air, and then also for the wall losses. The only other thing we need here is the cross-sectional area. You can have round tunnels, you can have semi-round tunnels, you can have rectangular tunnels. Another key, assume that CX is well mixed in vertical and into page directions, which means anywhere in here it's the same C, but it will change with X. This is a very small control volume of dimension dx. From last time, the distributed source equal the total source times dx over L, arguing that if you integrate from x equals 0 to L of S dx over L, you just get L over L times S, so you get S back. So we've just distributed that source into millions of little tiny sources along the length of the tunnel. We had called that little s last time, but I'm not going to use that because that conflicts with a notation that I'm going to use. Similarly, we want to do the same thing with these other variables, QM, QE, and wall losses. We're going to define a distributed makeup air volume flow rate, QM dx over L. So all we're doing is multiplying by dx over L. Distributed QE would be QE dx over L. And distributed wall losses, well, the wall loss when we did this with rooms was KW ASC, the wall loss coefficient times the surface area that absorbs contaminant times C times dx over L. Let's do our control volume from dx to x plus dx. I have my distributed source, S times dx over L, my distributed QM, my distributed QE, and my distributed wall loss. We have U and CX coming in, and what we're going to do is use a Taylor series expansion, truncated, keeping only first order terms. So it's U of X coming in at the left and U of X plus du dx times dx, since this distance is dx, coming out plus higher order terms times dx squared. We're ignoring all that stuff and do the same thing with C. Let's do conservation of mass balance of the contaminant in this little control volume. For a steady flow, remember C is only a function of X, and we have dropped the J subscript, but we're talking here about the contaminant. So we have sigma in m dot equal sigma out m dot. That's our mass balance. So we want to look at all the positive and all the negative terms. What do we have coming in? We have the source coming in. We have QM coming in with some CM, which is the makeup air mass concentration. Coming out, we have wall losses. We have QE with its concentration, which is C, just like we did with the room. This C is constant anywhere in this control volume vertically. It changes a little bit through the control volume, but what's coming out is C of X. And then, of course, there's some flow coming out that side. So we just add all those terms together. We have U coming in times C times AC. Remember, m dot J was equal to CJ times Q back when we used subscript J. So Q is just velocity times cross-sectional area plus our source plus makeup air coming in times C makeup. All these are in, and then we'll subtract all the terms that are going out. So minus U plus du dx dx times the concentration, which is now C plus dC dx dx times cross-sectional area. There is a wall loss, KW ASC dx over L. And then finally, we have the exhaust, so that's QE dx over L times C. This is C because what's coming out is C of X. These are all terms coming out. All of those have negative signs because they're removing contaminant from the control volume. And now let's expand this term. This term is very, very small. So we're going to neglect dx squared terms as dx goes to 0. This term and this term are the same, but there's a minus sign. So this term cancels this term. Multiply each term by 1 over dx AC, then rearrange. Let's call this whole grouping little s, that's a lowercase s. And similarly, we're going to call this QM over ACL, little qm, lowercase q. Call this QE, and we'll call this K. And now let's do a control volume analysis, same control volume of the bulk airflow. Notice that in general, if it's not balanced, we have a different U coming out than coming in. So I have to look at the bulk airflow. I have in and out on two separate sides here. That's what's coming in, and then this is what's coming out. This modified U, the U at the exit on the right, times AC plus QE dx over L. So that's our bulk airflow rate. And notice that these two terms, UAC and this one, cancel. And then we'll do a little bit more algebra, namely divide by AC dx. And I'll rearrange du dx equal qm over ACL minus QE over ACL. And we recognize these as QM and QE on the right-hand side. So this becomes du dx equal qm minus QE. For balanced ventilation case, qm is equal to QE. Therefore, du dx equals 0, so u equal constant, which we already know. But let's leave this in because a nice thing's going to happen here. And also it will be more general because we haven't really said yet that it's balanced. So this will actually work for the unbalanced case as well. I'm going to label this 3, and I'm going to label this equation 2. And notice that we have a du dx term here. So I'm going to plug 3 into 2 where that du dx is. And so when we write all that out, we get this. And notice now that we have QEC minus and QEC minus on both sides of the equation. So those cancel. So we actually got rid of QE. Even if we have unbalanced ventilation system where QE does not equal QM, that will be taken into account with that capital U because U then will be changing with X. So this is actually valid even for an unbalanced case. Another key is to write in standard form, and we see that this is a first order ODE. How do I know it's first order? Well, I see a dc dx. I don't see any d squared c dx squared terms, so that means it's first order, not second order. And this is a function only of x, so it's a first order ordinary differential equation. Now let's put this into standard form. The same standard form we had before, dc dx now equal b minus ac. So this is the same standard form we had before, except we used t. So we had a first order ODE where c equal c of t previously, and then here c equals c of x instead of t. But it's the same equation. We can write this in standard form. So let's do that. This equation becomes dc dx equal lowercase s plus qm cm over u minus k plus qm over u times c. And I'm going to write the way I used to do it with time, dc dx equal b minus ac. And so b is equal to little s plus qm cm over u, and a is k plus qm over u. And notice that just like we had in the ventilation cases, we always had a v in the denominator. Here we have a capital U in the denominator. If it's unbalanced, then u is a function of x. And then you typically will need to integrate this equation numerically using Runge-Kutta, for example. But if it is balanced, then qm equal qe, which means that u equal constant. All these other parameters are constant, so a and b are constant. And so for that case, we can solve analytically. So this is the solution for balanced transverse ventilation in a tunnel. C max equal B over A. When we were doing rooms, we would call that CSS. When T goes to infinity, well, this is now C max when X goes to infinity. And so plug in A and B. From here, the U's will cancel, just like the volumes used to cancel in our previous problems, room ventilation. So C max turns out to be little s plus QM CM divided by little k plus QM. And also at any x, remember we have that exponential function, we do the same equation except again now it's x instead of t. So C at any x is C max minus C naught. That's the value of C at x equals 0 times exp negative k plus qm over u times x. So remember, we used to have negative AT, now we have negative AX, but it's the same equation we had before. So let's plot C mass concentration versus X. C will reach some C max value. For a general case, C is going to behave like a first order ODE, so it's going to have an exponential growth and flatten out at C max, just like we always used to draw with time. These tunnels can be as long as we want. If L is here, then we would pretty much reach Cmax. Of course, you never really reach Cmax because it approaches it asymptotically. If you have a shorter tunnel, then you'll have some C of L that will be smaller than the maximum. So you don't always get to the maximum depending on how long your tunnel is. So let's do an example problem. I'm going to assume the worst case scenario, and that is the older version of EFC. U naught, CM, mass concentration of the makeup area. Wall absorption coefficient. Wall absorption is on the side walls and ceiling only, not on the floor. So we're going to have to analyze that a little carefully. We have a makeup air volume flow rate and exhaust air volume flow rate. This is balanced, obviously, since QM is equal to QE. PEL I looked up for CO is 55 milligram per cubic meter. Traffic density, VC is average automotive speed. C naught, concentration at the inlet, and then the dimensions of the tunnel, the width, the height, and the length. The first thing I want to do is think about wall adsorption or wall losses. And so let me sketch the cross section of this tunnel. We have a W width and we have a height H. L is into the page here. We're looking at a cross section. We have a KW ASC dx over L term, but it is going to the side walls and the ceiling, but not to the road, the bottom surface. So we have to be careful how we define this K term. AS, the area that we're adsorbing the contaminant, over ACL times KW. So here, there's two sides, so it's 2 times H plus 1 ceiling, which is W, times the total length into the page. That will give me the total adsorbing surface area. The cross-sectional area is H times W, and then there's an L in the denominator, and then there's a KW. The L's cancel, so my K will be 2H plus W over HW times KW. And if you plug in the numbers, you get 0.00312 over a minute. This is a strong suggestion. Do this problem in software and make sure you get my numbers correctly, and then you should have no problem doing the quiz. Similarly, capital S turns out to be 952,000 milligram per meter cubed. That's the total source strength. Lowercase s, and then QM. And that's also equal to QE. And then in our ODE, in standard form, we call that A was K plus QM over U. Plug in all our numbers, you should get 0.003164, and the units are 1 over meters. And then B is 0.122125 milligram per meters to the fourth. When you take B over A, which is our C max, this gives you milligram per meter cubed, which is correct. I have my units right. By the way, U is a constant, which was given as 80 meters per minute. And then finally, C max turns out to be 38.6 milligram per meter cubed. This is if L goes to infinity, we would eventually get there. Let's compare to PEL for CO, 55 milligram per meter cubed. So our Cmax is less than the PEL. For these kind of worst case conditions, the designers should be happy about that. I also asked at x equal L, calculate C. I wrote down this equation that we had previously and then plugged in all the numbers, 38.53 milligram per meter cubed. It's a little bit less than Cmax, but not much. Instead of 38.6, we have 38.5 basically. So in summary here, for this particular problem, C will go up to Cmax a little bit beyond that. And so we have a slightly smaller C than maximum.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.